Okay, we are back again. So, next we will see the reflected impedance, right, of two mutually your coupled coil, and after that we will see that numericals. So, in this case two coils are there, dot convention given, their mutual inductance is M, and this is one load impedance is their ZL. This is the primary coil, this is the secondary coil. Here resistance is R1, here resistance is R2, here inductance is L1 means reactance is j omega L1, here it is j omega L2 and mutual inductance is, and this is the voltage source. This circuit is closed actually, right, and current is taken I1 and I2. So, in that case if you look into that if you when in this coil the current is entering into the dot I1 current, this is I1 current because current is moving like this is I1 current. So, here current is entering dot, but in this case the I2 current, this current actually leaving the dot, right. So, this way you have to see first, right. So, that means sign will be that mutual you are what to call mutual inductance voltage generator, that sign will be negative because current here is entering, here it is leaving. So, based on that so little bit, and this is ZL, impedance ZL is given. Based on that, if you write in the first in this loop, if you write your KVL, so it will be V is equal to R1 plus J L omega L1 omega into I1 minus j omega m I2. I told you the sign will be minus because current here is entering and it is leaving, the way we have taken. This is equation 14 say, and here in this loop if you are, there is no voltage source here. So, 0 is equal to R2 plus j omega L2 plus ZL, because this is the load impedance is there ZL, right, I2 minus j omega m I1. This is this part due to the your mutual coupling, right. This is equation 15. Now, if you solve, I mean from here I2 you are getting from this equation 15 j omega m I1 upon R2 plus j omega L2 plus ZL. This is equation 16. So, from equation 14 and your 15 we get V upon R1. You please solve this one, right. I have written directly to save time. You please find out what is V upon I1. You will get R1 plus j omega L1 plus that this term you will get omega square m square divided by R2 plus j omega L2 plus ZL, right. This was the when mutual was not there. So, this is the your impedance of that coil 1 R1 plus j omega L1, right. So, this is actually we call V upon I1, this total we call the input impedance. So, this is input impedance and this is the impedance of the coil 1 without mutual inductor, right. Now, so therefore, Z input is equal to V upon I1 R1 plus j omega L1 plus this one. So, look, be due to the M only, when mutual coupling is not there, M is equal to 0. So, this term should not be there, it will be the only the your what you call the impedance of the coil 1, but due to that your what you call mutual inductance, this term is added. So, this is actually reflected impedance of the your coil your this thing of the circuit, that is omega square m square upon this one. This is equation 18, right. So, this is simple thing, only thing is that this one you solve and find it out. I have written the final expression, right. Now, next is induced EMF, very simple thing. Suppose you take flux is a sinusoidal one, say time varying, phi is equal to phi max sin omega t. So, V is equal to n d phi by dt. If you take the derivative of this one, you will get n phi max omega cos omega t, right, and omega is equal to 2 pi f. So, V is equal to 2 pi f n phi max cos omega t, right. There and this one and this one, this is the maximum voltage. So, divide this one by root 2, this is 2 pi f n phi max divide by root 2. So, it will be now root 2 pi f n phi max, this is 4.44 f n phi max, this is the RMS voltage. A simple thing, just for this thing I have written that phi is equal to flux is phi is equal to phi max sin omega t, then how the voltage will be induced, and we know V is equal to n d phi by dt. In coil you have n number of turns and phi is the flux linkage. So, this is the your RMS value of the voltage 4.44 f n phi max, right, because this term is divided by root 2. So, it will be 2 by root 2 will be root 2, right. Next we will take the numerical. Numericals are easy, only thing is the calculation should be correct. For example, this example 1 is taken, right. Just hold on, let me reduce the zoom little bit, right. So, this is that this is the problem. So, in that case first you see the problem. It is actually what is given, that you have to find this this is one your what to call this this is coil is on this part of this material, right, and number of turns N1 is 500, and here also N2 is equal to 1000 turns, right, and you have to consider your mean path. All the diamond mu r for this one is given, for this material is 1600, right, it is given, and you have to find out L1, L2, M1 to M21. Each coil is excited with 1 ampere current. I mean each coil is excited with 1 ampere current. We will only consider first this one, and how to take the mean length, how to take the dimension is given. This height from here to here it is given 4 centimeter, from this point to this point it is given 6 centimeter, and here the thickness is 1 centimeter. So from mean path we take, so this is actually 0.5 centimeter, this side also 0.5 centimeter, this also it is given from here to here 3 centimeter, from here to here it is 6 centimeter it is given, right, and side is actually your what you call sides are 3 into 3 centimeter each. So your right sides are 3 centimeter each. So and this not 2 centimeter each, right, it is 2 centimeter, this is 2 centimeter, right. So mean path will be this side. If you take from here, it will be here to here it is 1 centimeter. See carefully, everything is marked, and here also this is the 2 centimeter. So this mean path will take, so from here to here this gap is 1 centimeter, right, and here also 1 centimeter. So we have to find out, you have to what to call, we have the 3 different path, right, 3 different path, and this is from here is one from here to here, another is here this limb, and another is this limb, right. So there are 3 paths, right, and say both we say either of these coil is excited by 1 ampere current. First we consider only I1 is equal to 1 ampere, forget about this one. The turns here it is 500 and turns here is your 1000 turns. Independently we will see how things are, and here this your thickness of this is 1 centimeter. So that is why from here to here the mean path it is marked 0.5 centimeter, right. So everything is marked. Let me clear it. If you look at the diagram, everything is marked for you. Just see carefully how we have done it, right. So you have to find out. So you have to find out, this is figure 18, L1, L2, M1 to M21, each coil is excited with 1 ampere current. First we will see that coil 1 is excited with 1 ampere current, right. So now if you see that your what you call, that we know the reluctance is equal to L upon A mu, that we know, that is L upon A mu 0 mu r ampere turns Weber. Mu r is given 1600 for this material, same material, this 1600, right, and we know phi is equal to Fm by r, like your V by r I we find out, similarly phi is equal to Fm by r Weber. Now we have to, there are three different paths. So L1 if you see that this is actually mean path, this is actually 6, this is 6, right, and this side is 1 and this side is 1. This similarly this side and this side identical, right, this side and this side identical, and this side 4 plus 1 and your 4 plus your what you call, from here to here it is 1, here to here 1, right. This side it is there your 4, your what you call this from here to here it is 6 and here it is 1, here it is 1, right. So 6 plus 2 into your 2. So if you look into this, this sorry, L1 is equal to 6 plus 1 plus 0.5 into 2, or this side is actually this is 6, this side is 1, this side actually it is 0.5, this gap is actually 0.5. So and same is other side also, it is 6 plus 1 plus 0.5 into 2, not 1, 1 is total, here it is 0.5, the mean path, right. So plus just see this. So this is actually your into 2 plus 4 plus 2, I mean this side it is 4, and this side is your what you call, this side it is, this is 1 and this is also 1. So 4 plus 2, so this side actually 4 plus 2. So this is actually 4 plus 2 is equal to 21 centimeter, that is 0.21 meter. Similarly, if you come for L2, it is given 3 plus 1 plus 0.5 into 2, 4 plus 2, that is here it is 3, this side is 1, look at that, I am marking by pointer rather than pen, 3 plus 1, this side is 0.5. So 3 plus 1 plus 0.5, this side also 3 plus 1 by 0.5, so multiplied by 2, right, then plus 4, this side is 1 because here it is marked 1. So, this side is 1, this side is 1. I mean here it is written 1. So, same is here also it is your what you call 1 centimeter. So, this side also 1 centimeter. So, 4 plus 1 plus 1, right. So, uniform, it is uniform. So, here it is your L2 is equal to, then it is 15 centimeter, 0.15 meter. Now, L3 is the middle central limb, right. L3 it is 4 plus 2, this side is 1, this side is 1, this is the height, right. And this R1, R2, R3, R1 here, R2 here, this is the your reluctance of the 3 different portion, right. So, now L3 is equal to just 4 plus 2, 6 centimeter, 0.06 meter, and A is equal to sides 2 centimeter each. So, 2 into 2, 4 centimeter square, that is 4 into 10 to the minus 4 meter square. Therefore, reluctance for path 1 R1 is equal to L1 upon A mu 0 mu r. Mu r is given, right, and A is also known. So, substitute, you will get, this is the value of R1, 26,000, not 26,000, it is your what you call 2,61,113.5785 ampere turns per Weber, right. Similarly, for R2, if you calculate reluctance for path 2, this is for path 1, that means this path, right, that reluctance of this path. One is for this path, it is marked as like this, this is for this path you are getting reluctance of this is another reluctance, this is another reluctance, this is for R1, this is R2 and this is R3, 3 different paths, right, central limb and other 2 sides. So, here similarly for R2 you calculate L2 upon A mu 0 mu r, all are computed, substitute, you will get 186,509.7 ampere turns per Weber. Similarly, for R3 you will get 149,207.76 ampere turn per Weber. And we know that MMF for that coil 1 is excited by 1 ampere current and its turns is 500. We are not considering coil I2, right, just 1. So, FM1 is equal to 500 ampere turns. Now, if you look into that this is your circuit like a DC circuit. For example, that this is the direction of the flux, this is your direction of the flux, because you grasp the coil in the direction of the current, then thumb is the direction of the flux. So, this is the direction of the flux, right. Say total flux if it is phi 1, right, phi part is going here and part is going like your DC circuit, and this is their flux is flowing, right, the current flows, and as the direction of the flux is this way, that means this will be plus and this will be minus and that will be your FM, this way you do. That is your, you see the direction of the flux, and from plus your current actually coming out, so flux is coming out, this way you take, this is analogous, analogy to electric circuit, right. So, if it is so, then you look at the circuit, look at the things are very simple once you have calculated, look at that, this is phi 1, this is phi 2 and this is the phi 3, that this is the flux and this flux is divided into 2, these 2 are parallel path, right. So, and this is your MMF, that this is plus minus sign, I told you how you take, you grasp the conductor in the direction of the current, the thumb will be the direction of the flux. So, accordingly you can choose the polarity, this is your polarity, this is plus minus, this way you take, right. And same as resistance, you simply calculate the series parallel this thing. So, its reluctance will be equivalent to R1 plus these 2 are in parallel, R2 into R3 by R2 plus R3. With that you will get the reluctance of the complete your what you call complete circuit, right, the ampere turns per Weber. Therefore, phi 1, that is the current I1, you will get FM1 by reluctance. So, FM is equal to your 500 ampere turns that we have calculated, here it is 500 ampere turns. So, divided by this figure, that is getting 1.453 milliweber. This is your phi 1, right. Now, the way we do the current division, same way, that phi 2 actually phi 2 1, right, phi 2 is equal to this one, it is phi 2 1 is equal to, you can write that phi 1, this is the total flux into R3 divided by R3 plus R2, the current division that I have done, here also flux division. So, it will be 0.646 milliweber, very simple it is, only you have to understand a little bit, right. Nothing is there, looking at the diagram circuit, nothing is there, just see the direction of the flux, see the ampere turns and calculate all the reluctances value, dimensions correctly, right, and then you will get your what you call the correct answer, right, nothing is there actually, right. So, this is your what you call phi 1. Now, we know that earlier I told you, this relation is required, that Li is equal to n phi. So, same relation we are using, L1 is equal to n1 phi 1 upon I1. So, n1 is 500, right. Phi 1 we got 1.453 milliweber, and current I1 is actually this one in the diagram, it is showing I1, small I1, it is actually 1 ampere, not capital I1, so correction, right. So, it will be 0.7265 Henry, that is L1, and M21 is equal to your N2 into phi 21, that is equal to actually phi 2, because in the other coil there is no current, I2 is equal to 0, right. So, we are trying to find out M21 divided by I1, it will be small I1, it is actually 1 ampere, right. So, N2 is 1000 ampere in the second coil, and phi 21 is 0.646 your milliweber divided by 1 ampere. So, it is millihenry. So, 0.646 millihenry. So, very simple it is, right. So, similarly, you should compute this one L2 M12 by exciting coil 2, I2 is equal to 1 ampere, and take I1 is equal to 0. This you please do it of your own, right. Answers are not given. Example 2, when both the coils are excited by 1 ampere current, determine phi 3, right. So, question is that both the coils are excited. In that case, look, here is plus minus, here it is actually, if you look into that, here it is plus minus, but here it is plus minus, and 1 ampere current, both the coils are excited. So, this is 5 ampere turn, this is 1000 into 1, so 1000 ampere turn, this is R1, R2, R3, this way you have to compute phi 1, phi 2, phi 3. Now, look at this one, this is plus, this is minus, right, like you please come to that diagram. When both the coils are excited, right, in that case, look, this is the direction of the current, this is the current, right. By right hand you grab the conductor in the direction of your, what you call, in the direction of the current I2 in here, right, you grab it like this. So, thumb is moving downwards, that means this is the flux line. So, this is your flux, your phi 2, right. So, as it is downward means this is plus and this is minus, as if the way current comes out from the positive terminal, here also the flux direction, that is why this is plus, this is minus. That is why in the direct, and that is why in the diagram, that is why in this diagram you are taken this one, everything I have given to you. So, these are the answer, phi 1, phi 2, phi 3, this one the answer. You please all the reluctance, everything computed. So, please solve it for yourself, answers are given for this one, right. Now, example 3, this is also one, here is one limb is there, this is 17 centimeters, right, this is 2 millimeter, this gap is 2 millimeter, and one coil is there, it is wound like this, both the coil, this side 1000 ton, this side is 1000 tons, here it is from here to here, the length is given 10 centimeter. So, you have to, what you call, you have to see the mean length. So, this is from here to here 20 centimeter, and this 3 centimeter side, if 3 centimeter side means, that means 3 centimeter side means this mean length, that means this is actually this portion actually 1.5, this is also 1.5. So, 10 minus 1.5, so 8.5, this is the mid length, that is mean height, right, 8.5, and this is 20, but 3, your what you call, it is your 3 centimeter side, it is written here 3 centimeter side, with this side 1.5 and this side also 1.5, that means mean length will be this side from here to here 20 minus 1.5 minus 1.5, that is equal to 17 centimeter, right. And this is already mean length is given, everything is computed, gap is 2, right, and this is your what you call, we have to find out flux and other things. So, if you look into this and look into this, that your there are 3 paths, one LB, then your LC, and this is LA. This is, look at the pointer, this is LA, the gap is your LC, and here it is, this path is LB, right, it is marked B, it is A, and this gap here it is marked C, look at the pointer, right. Therefore, mu RA is given 1000 for your for this material, and mu RB is 1200 for this material, right. So, A is equal to 3 centimeter side, so it is 9 into 10 to the minus 4 meter square, right. LA is equal to 17 centimeter, that is 0.17 meter. LB is equal to your, this is I told you, this 17 plus 8.5 plus this side also 8.5. So 17 plus 8.5 plus 8.5 centimeter is equal to 0.34 meter. So reluctance formula LA upon A mu 0 mu RA. So you will get this value. Similarly, RB is equal to LB upon A mu 0 mu RB. Substitute all the values. Mu 0 you know 4 pi into 10 to the power minus 7. You substitute all, you will get this value, and RC will be, you will get 2 LC upon A mu 0, right. Yeah, that is your what you will get, that is your whatever it comes, that it is 2 millimeter. So 0.002 meter divided by this one, right. So is equal to, you will get your this thing. So why RC is equal to 2 is taken, this side one gap, this side also one gap, that is why it is multiplied by 2 into, right. This is 2 millimeter gap, here also 2 millimeter gap. So that is why 2 into LC. So it is your what you call, this much value is coming. So total MMF will be coils excited by 1 ampere current. So this side your what you call 1000 ton, this is 1000 ton and excited by 1 ampere current, right. So in this case it is your 2000 ampere turns. So phi is equal to MMF by reluctance, total reluctance we got this one. So phi is equal to MMF by reluctance is equal to this much of Weber, and flux density B is equal to phi by A. So this is phi, cross sectional area is 9 into 10 to the power minus 4 meter square. So this is 0.564 Weber per meter square, right. Hope you have understood this, right. There is absolutely no problem. Take some problem from the same book and please do it yourself, some problem. Take some good book and see that you are solving it. Similarly, this one I will not tell you anything, this I leave it to you. A circuit is shown, right, that your that's here you have n number of turns, n1 number of turns, n2 number of turns, mutual dot, nothing is shown, something you put, I have made it something, and all these two equations I have written, right. So you check whether it is correct or not. This is everything is correct, but you check this is given to you, right. Look at that. Sometimes you should not be confused looking at such kind of electrical, such kind of circuit. See carefully how this is connected and accordingly you will do it. Now example 5, there this problem I have taken from one book. So this this problem I mean you have to see how things are, right. So all these things actually this your direction of the current was not marked in the book, this I have made it, and this is 5 ohm, and your self reactance here reactance is also 5 ohm, and here also 5 ohm, here also reactance 5 ohm, mutual reactance is J2 ohm, it is given, and here voltage is given 10 angle 0 degree, here it is given 10 angle 90 degree volt. Probability is marked, one capacitor is there, capacitive reactance is minus J10 ohm, you have to find out voltage across the capacitor, that is Vc is how much, that you suppose you have to compute. And this way I have taken that loops or this thing, the way I have taken, this is one is I1 and this is one is like taken I2, right. So if you take like this, then I1 plus I2 flowing through this, right, because we have taken like this. So if you now this is actually what dots and other things not mentioned. So here dot convention is taken, right. So current is entering here, here is dot is taken, right, and in this case your what you call another dot is taken here, another dot is taken here, right. Say current is your what you call leaving, and here it is taken that current is entering, these two dots we have taken. So this dot thing is taken, right. So this way I mean this, that means I1 plus I2 current entering into the dot, and this I2 current actually it is your this is the current I2 we have taken like this. So this is actually I2, this is taken like this, right. Suppose it is leaving the dot. So if it is so, then look at the flux direction. Now in the direction of the flux for this winding, I1 plus I2 entering. So if you direction of the flux, then if you grab it, it is actually going like this. This is phi 1, and in this case, now in this case what is happening, that current is leaving the dot, right. As the current is leaving the dot, then in the direction of the current, if I wrap it the way on the left hand side, right hand side, if I wrap or grab the coil like this, the direction of flux is upward, that is why phi 2 is upward. So phi 1 this way and phi 2 is this way, that means they are opposing each other, isn't it. That means your when you write the equation, it is entering the dot, it is leaving the dot, that mutual thing will be negative sign, right. So if you write the equation, look, it takes time. So this is the equivalent circuit, right. This 10 volt, this thing, 5 ohm, J 5 ohm. This mutual inductance between this one is entering the dot in the coil, another is leaving the dot, and this is 5 ohm. Now you can solve it by putting this thing because two coils are there, right. So repetition will be there, isn't it? So, but question is put the KVL in the first equation. It will be 5 plus J 5 into I 1 plus I 2, because here this is that your I 2 and this is the I 1. So current flowing through this, actually look at the pointer, it is I 1 plus I 2. So 5 plus J 5 into I 1 plus I 2. Now minus your mutual will come later, minus this is J 10 reactance into your I 1, because current in this loop. So this is minus J 10 into I 1, right. Then that current your what you call entering the dot, and I 1 plus I 2 entering the dot, I 2 is leaving the dot. So it will be, for this loop it will be minus J 2 into your I 2, right, because in this coil voltage induced due to I 2, it will be minus J 2 into I 2, that is 10 angle 0, right. So this is this is the voltage 10. This is one equation. Similarly, for your second one, when you apply your what you call now this is the second your what you call, this is the second loop. I mean we are covering like this. So in that case both the coils this current your I 1 plus I 2 flowing through this and I 2 is flowing through this. So look how things are. It will be 5 plus J 5 I 1 plus I 2, right. Then here if you come, it will be 5 plus J 5 I 2, right. This voltage will come later. Now let us consider the mutual inductance. Now it will be this coil, in this coil voltage will be induced due to I 1 plus I 2, but it is entering into the dot, leaving the dot. So minus sign. So minus J 2 mutual your reactance is J 2 minus J 2 into I 1 plus I 2. Now next is voltage induced or what you call in this coil due to the current here I 2 will be minus J 2. Look at the arrow here, it is upward, I have made it or what you call minus J 2 into I 2, right. Here it is minus, then minus J 2 into I 2, then plus 10 90 degree angle 90 degree minus 10 angle 0 degree. So this is equation 2, this is equation 1. You solve for I 1 and I 2, right. I hope you have understood this, right. I hope you have understood this. I mean if you have understood if you have understood this problem, then absolutely there is no problem for solving any other problem on magnetic circuit, right. Just you have to see the dot convention. So in this case, so if you solve for equation 1 and 2, you will get I 1 is equal to 1.015 angle 113.96 degree ampere. Look, whole solutions I have, but here I did not put it. It will consume more time. This is an exercise for you, please do it, right. It will take some time, it will do it, right. And then VC will be, this is the current, this current I 1 is flowing through this. This is the current I 1 is flowing through this. VC will be this your I 1 into minus J 10, right. That is what is written here. This is I 1 into minus J 10. So it is I 1 is 113.96 degree and minus J 10 means it is your 1.015 113.96 into 10 angle minus 90 degree. So minus 90 plus 113.96. So it will be your 10.15 angle 23.96 degree volt, right. This is the answer. Now this one, when 3 dots are there, 3 dots, let me tell you one thing, for the exam purpose 3 dots are little bit heavy because of time consumption, right. So question is that, but this when 3 dots are there, this all these equations I have written, right. You please write it. I am not explaining now, all are correct, it will save my time. So see how at least you will learn that how I have written this, all mutual things are given, their cyclic current is given the way I have taken, right. And just see this, all these equations I have written for you. Just see the circuit, draw the circuit first, then you see the equations how I have written, right. And see all these things written, everything is actually correct. So please write yourself first, then you see this, then you see what has been written, then some time will be saved, right. And in the frequency domain, I told you earlier, d by dt you replace by j omega, right. If you do so, your equation will be like this, right. All these equations will be like this, and ultimately your equivalent circuit will be like this, right. So this one you please make it of your own, right. You write down all these equations of your own. First you draw the circuit, then you write down all this your you pause it and then draw the circuit, then all these equations you write one by one, right, and then you frequency domain you d dt you replace by j omega, and then you will your what you call, then you see this one equivalent one. This is an exercise for you, all everything is given in front of you, right. Next is, this is another problem. This problem is very interesting problem. Two coupled coils with respective self inductances L1 is 0.05 Henry and L2 is equal to 0.2 Henry, right, have a coupling coefficient K is equal to 0.5. Coil 2 has 1000 turns. If the current in coil 1 is I1 is given 5 sin 400 t, that is omega is equal to 400, right, so ampere, determine the voltage at coil 2 and the maximum flux set up by coil 1. So, solution, we know that K is equal to m by root over L1 L2, right, that is A or m by root over L1 L2 K. So, m is equal to K into root over L1 L2. So, K is given 0.5 and your L1 L2 given root over 0.05 into root over into 0.2. So, m will become, mutual inductance will become 0.05 Henry. Now, voltage of coil 2 is given by, we know that V in coil 2 m into di1 upon dt. So, m is 0.05 and I1 is given 5 sin 400 t. So, if you take the derivative, V2 will become 100 cosine 400 t, right. So, that means also V2 we know is equal to N2 d phi 1 2 upon dt, that we know, but we have got it V2 is equal to 1000 cos 400 your t, right. So, now in this case V2 you substitute here, N2 is known and you have to integrate. So, 100 cos 400 t, N2 is 1000 turns, it is given d phi 1 2 upon dt, or phi 1 2 is equal to your divided by your what you call 1000. So, 10 to the power minus 3 into 100 cos 400 t dt. If you integrate this, phi 1 2 will be 0.25 into 10 to the minus 3 sin 400 t Weber, right. So, that means phi max will be 0.25 into 10 to the minus 3 Weber. This is the phi max, 0.25 milli Weber, right. So, that means K is equal to, we know that phi 1 2 upon phi 1. Phi 1 is the total flux and phi 1 2 is the flux linking the other coil. So, K actually is equal to phi 1 2 upon phi 1 or is equal to phi 2 upon phi 2, that is phi 2 the total flux and your flux 1, your phi 1 is the link, your in coil 1 that phi 1 is the flux linkage. So, either you can write K is equal to phi 1 2 upon phi 1 or phi 2 on phi 2. This is also coupling coefficient. This you should know this, right. We have seen earlier in the diagram, right, phi 1 is equal to phi 1 1 plus phi 1 2, right. That means K is equal to phi 1 2 upon phi 1 or vice versa. Or you can put that same philosophy, or you can put phi 1 max is equal to phi 1 2 max upon K. From here you can, from this equation you can write phi 1 is equal to phi 1 2 upon K, or you can write phi 1 max is equal to phi 1 2 max upon K. Same thing, you will get 0.25 by 0.5 your milliweber, because K is equal to 0.5. Therefore, phi 1 max is equal to 0.5 milliweber, right. So, this problem is interesting problem and very simple problem. So, now this one, determine the voltage across the 5 ohm resistor for the dots given in the diagram, then reverse the polarity in one coil and repeat. So, this is the problem is given, this is the problem is given that your J is equal, K is equal to coupling coefficient 0.88, J is equal to given, everything is given, right. So, this whole solution is there, whole solution is there, I am not telling all these things. So, you have been asked to find out the voltage across the 5 ohm resistance, right. So, all this your XL1 5 ohm, XL2 5 ohm, that K is equal to computed m by root over L1 L2, right, everything is given, right. So, omega m, then K up to this thing I am showing you, this is computed, right. Rest is you please solve it, right. I suggest you please solve it. Dot convention is given, the current is entering the dot, leaving the dot, that means when you write that your what you call the similar problem also shown you earlier, right, similar problem. So, when you talking, when you are considering for second your this loop bigger one, when you are considering the whole one, at that time you see the repetition will be there for the mutual induced mutual voltage, right. So, you please solve it, answers I am not telling, you solve it when you read this video lecture, you solve it and your what you call, and at that time you ask the answer whether you have got the correct answer or not. I'll give you the correct answer, but put everything in the forum. So now magnetic circuit is over. Now my question is that when you will come up to this listening that DC circuit, single phase AC circuit, 3-phase AC circuit, resonance, maximum power transfer theorem and magnetic circuit, my suggestion is that you take not too many books, no need to pick up too many books, you take 1 or 2 good books, they solve few examples and practice little bit more, right, practice little bit more and just see whether you have been able to solve it or not. If you have any doubt or anything, you ask in the forum, we will answer it, you will clear your doubt, and we will answer your what you call all your queries, right. Whatever question comes to your mind, you put in the forum, we will answer all your queries. With that, this magnetic circuit is over. Next we will take the single phase transformer. As the magnetic circuit is over, you will find single phase transformer is very easy. You will really find it is very easy, not at all difficult one. With that, thank you very much. We will be back again.